Okay, so there we are. Since I had to stop in the middle of the proof of this construction, it makes sense, I think, to recap briefly where we are. So let me go all the way back to this. Okay, that was all the circuits part. Yeah, lots of clicking. We're in the chapter of randomized complexity theory. So the objects of study are algorithms that use randomization, our probabilistic Turing machines. And one key question you could have is there anything you can do with these probabilistic Turing machines in polynomial time that you cannot do with a deterministic algorithm in polynomial time? And even in the most general case where we allow the algorithm the randomized algorithm to output the wrong result occasionally. And one reason why this might not be the case is if you use very few random bits, you can de-randomize the algorithm by simulating all possible runs for all possible inputs of random bit strings. And if you do the math of what that means, of how many random bits you could have for this to still work, you can work out that c times log n, some constant times log n, random bits would immediately work because it gives you a polynomial number of repetitions. Now that alone is not very useful because almost never you only need a logarithmic number of random bits to do anything interesting. But it immediately gives the question, what if the algorithm doesn't actually need the full randomness? Can we somehow give it something that looks random to the algorithm, but is actually computed from a small random seed? Then we would only jump to, well, we would only go through all possible seeds and simulate the computation on those and not on all possible strings. Now to formalize that, we needed two things. We needed a new model of computation, namely these Boolean circuits. They'll only pop up as kind of black boxes in the remaining parts, so it's not so critical to revise all the details there. But I wanted to show the two key definitions to formalize what this cunning character there had in mind. If you have some supposedly random bits R, and you compare on every possible circuit, every possible algorithm. Here for circuits is a certain size, how many gates it has. For an algorithm, it would mean the running time. So if all efficient, small or fast algorithms cannot sensibly distinguish between being run on these truly random bits or being or being run on these fake random bits, then by all intents and purposes, we call those random. We call them specifically pseudo-random with these parameters. And then the pseudo-random generator is an algorithm that outputs such random bits, but you can give it as many seed bits as you need, and it'll produce from L seed bits, it'll produce S of L pseudo-random bits, and they're pseudo-random with these specific parameters. Again, the choice of the parameters is not as critical, but you need to fix something to make a formal definition and a formal proof work. And then we've seen that essentially you need a pseudo-random generator of this quality. It can exponentially blow up the number of bits that you have from L to some constant to the L. And that's enough to de-randomize all of BPP, all polytime two-sided error Monte Carlo algorithms with bounded error. And the obvious thing worked. This is essentially the algorithm that we discussed last time. You go through all possible random seeds, you feed these into the pseudo-random generator, and use the output for our randomized algorithm. And then you just output the majority of all those pseudo-randomly many runs. And we've shown that if this would somehow fail to give the right answer, we would have distinguisher for these pseudo-random generators. But if that is an actual pseudo-random generator, that cannot exist. All right. Now we'll come back to discussing what this means for algorithms. The next unit will talk a bit about that in more detail. The key part for this unit is to look into this black box that we've used so far, that you can really exponentially blow up these random bits that you're starting with and get something that still looks random or random enough, sufficiently random. And that's this construction from Nisan-Wigderson. Yeah, maybe that's a good point to jump in also for the recording part. We left off proving the Nisan-Wigderson pseudo-random generator construction works. And just to briefly recap, we're essentially after a statement like this in a slightly weaker form. We'll only show this for specifically exponential functions s. The key idea of the generator is, in a way, super simple. We take our small number of seed random bits. We apply a hard function, so specifically in the sense of circuit complexity, even if you're only trying to compute this function for more than half of the inputs correctly, then you need a circuit of a certain size. If you have such a function, then we apply this, and for each input, we generate one pseudo-random output bit. And what we feed into the function is a certain specifically selected subset of the bits in Z. That's what I was trying to draw here. And where we left off yesterday is proving that there is a way to pick subsets with the properties stated in this definition. So there's, if you pick parameters L, N, and D correctly, then you can pick M subsets out of a subset of size L. Indeed, you can pick exponentially many. They're all of size N, the other parameter given, and their pairwise intersection is never bigger than D positions. And we've seen a specific choice of parameters, or more correctly, I guess, under some assumptions on the parameters, in particular that L is a good deal bigger than N. You can do a very simple brute force construction algorithm, and that finds such a design. This part, I won't go over the proof again. The next step towards generating this pseudo-random generator is a kind of intermediate step to make it a little easier to go about the proof. In general, we would have to show that the pseudo-random generator has the properties from the definition, namely it generates a sequence of bits so that no circuit up to a certain size can behave very differently on these bits as a whole as compared to really random bits. It's a lot easier to prove this intermediate step where you say I have a sequence of random bits. One way to say they're random intuitively is that whenever I have a prefix of the pseudo-random bits, so maybe here this is all of our, how do we call it, G of Z, for Z the seed, right? Do I have a name for the output already? Not really, right? Let me just cheat and look if I already used the name Y. So let's call this Y. It's a long sequence of bits. We'll use it for pseudo-random bits, but of course the definition is kind of general. If you see a prefix of those, so you see these parts, you don't know what this is. If these are supposed to be random, then it must be hard to take the next position I and predict it from all the previous positions. If that was easily possible for all the positions, certainly the thing isn't random. So the first step is this definition that we say some function, it'll be our pseudo-random generator in the end, has a similar setup as the pseudo-random generator for that purpose. So it's a function that maps binary strings to binary strings, and it blows them up. So if you input L initial bits, you get S of L bits out. That's the parameters how we used it before. And then we call this, this function g unpredictable if there's some constant, and every position I is such that you cannot predict the ith bit from just knowing the bits up to position I minus 1. And formally, what does predict mean? It means for every circuit up to a certain size, you cannot get, if you put in real random bits and compute your y from that, you cannot predict the next bit better than 1/2 plus a little bit. So 1/2 is always possible. You can just guess randomly. You could output a random bit and say that's my prediction. That's going to be right half the time. Or you can't expect it to be wrong more than half of the time for every possible bit. But the definition says no matter what you do, no matter what circuit you put in, if it's small enough, no matter how long the prefix is that you give me, the probability to correctly predict the next bit is just slightly above 1/2. And you already see that if you have a function s that grows very quickly, then this is actually a minuscule little probability on top of 1/2. Was maybe not obvious from the definition. I mean, it's stated on the slide, but I think it's clear if the input is pseudo-random, then this unpredictability should hold, because intuitively, if you could predict every position from the previous one, you could just regenerate the random string, and that's not exactly random. It's not so clear why this would be enough if some function is unpredictable in this more specific sense, that every single bit is unpredictable, that the whole thing would be pseudo-random according to our definition from earlier. But indeed, that's the case. It's a non-trivial result, so we'll have a theorem for that. And I'll give you some sketch of the proof, but not the full detailed computations in this case. But they're not very hard. It's more like the main contribution was coming up with the right definitions and making this connection, I think. So the formal statement is you have some stretch function s. How many more bits do you generate out of L seed bits? And we have a function g. So it just means this part, it maps from binary strings to binary strings. Its output is s of L when L is the input. And it's polytime computable. So I guess polynomial in the output size, though. I think this has to be taken with a grain of salt. If the output is supposed to be exponentially bigger, but then a polynomial of the output, I think what we want is we could probably do with a much weaker restriction. Let me replace this with 2 to the O of L, which sounds like a lot. We'll mostly use this for small l, so this will be polynomial in terms of the the algorithm's input that we use it in. But the function itself, it cannot be polynomial time in its input size, simply because it produces such a big output. Okay, so let's take function p as above. The function s can be polytime computable. Okay, that's fine. But g needs to at least produce its output. If it's unpredictable, then it is a pseudo-random generator, and of course with the same stretch. So how can we prove this? Basically by a contradiction and constructing some circuit again that distinguishes the pseudo-random bits from the real random bits. So again, assume we have that this function is unpredictable, but still it doesn't work as a pseudo-random generator. That means there must be some circuit that behaves differently on the output. So circuit C behaves substantially different on real random bits, and on real random bits is this part, and on the output of G on real random bits, but only L of them. And what this formally means is that the probability that they are the same is less than 1/10. So that's from all the way back. I want to flick through a million slides. So the probability that C on, let's give this a name. Let's say this is Z and this is Y. Let's call it R, like before. R. And the difference between that must be at least 1/10. That's what this substantially different is supposed to mean. That's exactly taken from the definition of pseudo-random. And if we say there's a circuit that distinguishes them, we mean the probability that it behaves differently is at least 1/10. All right. Now, what we have to do is from this somehow derive a contradiction, and what we'll do is we'll construct a distinguisher that shows that G is not unpredictable, that it is predictable. And again, for predictable, maybe it would be good to have the definition here. Sorry, messed up. Wrong slide. That one. So it's unpredictable if for every position I and every small circuit, the probability that the circuit correctly predicts the ith bit is small. So to counter that, it will eventually be enough to show that for one position I, it doesn't work. Is there a question? Okay. It will be enough to find one position I where we can correctly predict the next bit with a larger probability. But the construction is only probabilistic in that sense. So we only show there is an I, we can't name it. So we'll start with, for every position I, we'll build a predictor circuit, BI, that's using C and tries to predict the next bit. So how would it do that? The idea is, again, C is maybe draw some pictures up here. C is some unknown box that takes in random bits, or takes in some bits that it hopes to be random. And so I'm putting in R, the real random bits, which are all unknown. And I'm comparing it to feeding to C this much shorter random bit string Z, which I'm blowing up by G to the same size as what I had before. So it's pseudo-random, and I feed that in. Now, by assumption, this is actually not not always the same. There's indeed a good probability that C behaves differently. But I don't know on which input, so it's kind of tricky. And now what I'm trying to build, this BI, it's supposed to take the first I minus 1 of these bits up here. So the prefix up there is prefix here or prefix here, we don't know. And we're trying to predict the next bit. Now, we don't really have a way to call C with fewer inputs than it needs. We have to fill in some values. And so what we do is we fill up this rest of the space with truly random bits. And for the left part here, of course, this is exactly what we would have done before anyways. But for the right part, it might make things a bit different. So I'm kind of deviating from this scenario. So I don't know if the output of C will still be very different. But either way, I can simulate C using this mixture of pseudo-random bits and real random bits. And for each I get a slightly different mixture. But the idea then is if C outputs 1, then I'm going to output this single random bit that is here the first of the ones I add, and otherwise 1 minus that. And so the thing is, I'm doing this for both cases. So if I'm on the left, this is it's going to be equally likely to work out, whatever C does here. Whereas on the right, this might be a different outcome. Okay, so I don't know. This is that was very clear. The trick to observe is if you compare what these different B's run on, then for small I, you essentially feed only random bits. And for the last BI, you feed the entire string of pseudo-random bits, maybe except for the last one. So if you remember this picture here, at the very end, between, you could say this corresponds, come on. The left picture, where you do real random bits, corresponds to I equals 0. And the original right picture, where you feed in the pseudo-random bits, is I equals S of L. So for those, we know that C behaves differently. So as we increase I slowly from 0 to S of L, at some point, something must be happening. There must be some I where things are different, or at least it cannot be that all of those guess correctly with essentially spreading out this 1/10 difference over all the S of L steps. I'm making from I equals 0 to I equals S of L. I could map the difference in the probability to output a 1 between BI and BI minus 1. Is there a better way to draw that? Let's try to draw it this way. So I is on the x-axis. And this one would be the difference in probability. So probability of C with this weird input let me define a shorthand for that. That's gonna get too chaotic. Let's say pi is difference. Okay, di, the difference in probability between this input and the next larger I. Is the y missing? Come on. y1 up to I minus 1, followed by the random bits from z. That's the one probability that the output of this thing is 1. And I'm subtracting the probability for the same, but with a different I, okay? I'll say, let's do I minus 2 here, and then z minus 1 up to S of L. 1, close, and yeah, absolute value doesn't fit. Okay, that would never have fit on this axis down here. So let's put d of I on this axis. Now we know between I equals 0 and I equals S of L, there must be some movement of 1 over 10. And I'm steadily moving up here. So it's not possible that none of the steps from I to I plus 1 are at least this 1 over 10 divided by S of L. Because in total, they sum up to 1 over 10. And so in the best case, it's evenly spread out. Then I would get this. More likely is that some jumps are larger, some are smaller, maybe even some are positive and negative. But there must be one where in absolute value I'm changing by more than this. Okay, that's why I called it a proof sketch. Didn't want to do the full math detail, but I guess that's already giving you the main idea. It's just not possible that you don't have any I where this jumps by more. And that's almost what we need. It means there is some index I where our predictor for the next bit, given the previous pseudo-random bits filled up with real random bits, there's some I where this correctly predicts the next pseudo-random bit with this probability. Still just a tiny bit over 1/2 plus epsilon over S of L. But this was the definition of predictable, if you remember. There we had exactly this term, which of course is kind of chosen to match this proof. But so we've shown that G is not unpredictable. The term's predictable. And so that means our assumption must have been false, which means G is actually a pseudo-random generator. So zoom out of the bit chaotic proof. If as soon as you show that some function is unpredictable, it already will be a pseudo-random generator. So in the proof of the next part, we can restrict to showing just this next bit prediction that is unlikely to be correct. And that's the basically last step of the construction. What we'll still have to do at the end is pick all these parameters. That's what we'll come back to. Because there's L, there's N, there's D, there's M, and F and S, and it gets all a bit messy. The thing is, the proofs are cleaner if you keep the parameters generic. So bear with me for 2 more slides, and then we'll make things more concrete. The beauty is you can, in this general setup, can show that you get some pseudo-random bits out of this. So the main key here, the main message is, if you take this Nisan-Victorson construction as we've seen, take your function f, that's supposed to be a hard function, meaning even if you're only taking this average case notion, you need a circuit of size at least 2 to the 2 to the d, where d is some parameter. Then if you feed that into our construction and you use a combinatorial design with the parameters ln and d, so many of these subsets of the seed bits, then what you get as an output is a pseudo-random sequence of bits with epsilon of 1/10 and the guarantee of how large do the distinguishing circuits have to be before they can distinguish this sequence from real random bits of effectively this hardness of the function. Again, we lose this constant factor 1/10, but these are all in the end not important. Okay, so how are we possibly going to show this? Of course, we're going to use what we've just shown, Yau's theorem. So we won't show that this is pseudo-random. We will show that it's unpredictable. So that's the first step. We'll show that this Nisan-Victorson predictor is unpredictable. And based on that, we will show that if we had some predictor circuit for this unpredictable function, so again, proof by contradiction, assume that it's not unpredictable, that it is predictable. That means there is a circuit that predicts one of the ith bits. And from that, we will construct a small circuit for f in this weird average sense. So maybe you can see how this will fit together at the end. But the point is, you can build a small circuit for f that violates this assumption on its hardness. And that's where this all fits together. Again, I haven't stated that today. The assumption that there are functions with a high, exponentially high, in the end, average circuit hardness is a conjecture or is a hypothesis that we don't have a proof for. But there's some, we discussed a bit more yesterday, there's some indications that these are likely to exist. Okay, so let's do this. First step, let's give this hardness the name it had before. S is a function. So here f is again, you should imagine f to be a function that can take inputs of different sizes. And then the hardness also depends on the input size. So S is really a function of the input size. And the input size for F will be N. This is different from the L before, so I'm just going to point that out. I probably should, so S is used for different things. It's the size of the circuit, and so it makes sense to be used for the hardness of the function. We also used it as the, what did I call it? The stretch of a generator, so how many more bits it generates. Their S also made sense, but it will be a different S here. So the stretch of our generator will not be this S at the very end. Okay, that's a bit of a warning. So keep in mind the parameters. N is what we'll put into the function f. It's on the slides. I'm just trying to, I don't know, we should maybe keep some legend on the side. Okay, S is the hardness of the function. So intuitively, if f, to compute the value of f on inputs of size n, you need a circuit at least as large as S of n. And again, computing here just means in the sense of Monte Carlo algorithm, it's okay to be wrong on a bit less than half of the inputs. And the specific requirement from this average hardness was you have to be correct for 1/2 plus 1 over S, a fraction of all inputs. Okay, just rewriting the definition. Now we're trying to prove that this is refute the circuit predictability. Okay, we assume it's unpredictable. No, we assume it's predictable. Is this double negation too much now? think this might be less or equal. We assume there's a circuit and some position where we can't predict the next bit. And the thing, it has to match with the definition of unpredictable, this one. And it says that every position must be unpredictable. Only then is the function unpredictable. And to show that overall, the predictor is unpredictable, we do a proof by contradiction, assuming that it is predictable. So assume it was not predictable. Yeah, I don't know, this formulation I don't like anymore. But suppose it's not unpredictable, that means there must be an index that is predictable. So there's some position I and a circuit of a small size. And again, this has to fit. I wish again we had this here. So even if it's too small to read, what I underlined here is circuits of size at most 2 s of n. S here was the stretch. So if you output s of n bits, then you're supposed to have hardness against circuits up to size 2 times s of n. The size of the output of our Nisan-Wigderson predictor is m. That's the number of sets in the design. That's the number of output bits. So we need a circuit that's less than 2m to match that definition. Let's say assume towards a contradiction. That the NW generator is predictable. I think I tried to avoid writing predictable because we formally only defined unpredictable, so I should say not unpredictable. I guess that's what, but this is also writing predictable. Let's say, okay, assume it's predictable, then that means there's this circuit. And what's true for that circuit? Well, it's, sorry, the greater equal was correct. It can predict the next bit, so its probability to be correct is larger than 1/2 plus 1 over 10m. Again, m is the S of L from the unpredictability definition. And here R are the pseudo-random bits, and these are computed based on Z. Okay? So far is really just plugging in the definitions and not being lost in all the formal statements. Now, at this point, we have to plug in what we know about how the construction works. And that's, remember the picture with, we have L input bits, and then we pick subsets, feed them into F, and that each gets one output bit of the NW predictor or generator. So also our Ri, the ith bit that we try to predict, is the output of our hard function F on some subset of these truly random bits. And now to make life a bit convenient, let's just assume we rename the variables if necessary, so that this ith bit that we care about now is indeed computed just from the first n bits of the pseudo-random string, so of the random seed. If that wasn't the case, you can rename the variables instead to make it so. This is not a problem. They're random anyway, so they're fully symmetric. I will only do this once. So to write it more conveniently, there's now from Z, there's a prefix of size n. These are used in computing the ith bit, and only those. And then there's a long part, L minus n, and that's what we call Z2 here. So Z1 is these first bits, Z2 is the others. And not much has changed. I'm just taking this probability and plugging in what I know now for Ri. It's the function computed on set 1, the first n bits. For all the other bits, the R1 up to Ri minus 1, these are still computed from some subsets of the overall bits. They may use sum of set 1. They will mostly use sum of set 2, because the design can only have d things in overlap. But exactly spelling out which ones we don't actually need. And the rest is just copied. Okay. Now at this point, it looks like we're stuck in the sense that there's various things going on, and these are not independent. I cannot say that this bit here is in any way independent as a random variable from these other random bits in the prefix, because they are partly computed from the same seed bits. That's exactly the point of this design. They can overlap with up to d bits, but maybe this overlap with d bits is enough to create enough dependence that we can't predict, or that we can predict. Sorry. But in principle, it could be that if you base it on the same seed bits, that then the output becomes predictable. And the reason why that's not the case in the end is that d is small enough. But how to make progress on this one? In particular, because set 2 is also random. We don't really know what it is. But there's a clever trick, which I think in the end is just the probabilistic method in disguise. But you can abstractly state it. It's known as the averaging principle. And I'll connect it to this one, to this task in a second. Suppose you have some event on some random event that depends on 2 random variables. And we care about the probability of that event happening. Then we can always find some specific choice for the first random variable, so that the probability remaining, so you fix x to be that specific value, that's what I mean here. Little x is a fixed value, capital X is random variable. So you fix x to be that specific value and only average over the possible choices for y. And then the probability for the resulting conditioned event is never smaller than where you have the total expectation. And effectively, the probabilistic method just means if this is really an expected value, right? It's the expectation over both x and y of this indicator random variable for the event A of x and y. And an expected value, it cannot be that all possible values that the random variable can take are strictly smaller than the expected value. There must be one choice for x where the expectation on the left is at least as big as the overall expectation. And that's the probabilistic method. Okay, so it's nothing really fancy at play. The usefulness of this thing is that it's so general and you can apply it to all sorts of events. And specifically, we'll stick it onto this event, namely that our circuit on some weirdly defined random bits is the same as this other random bit where there's some dependence between them. Again, here the important part, maybe the important bit here in the averaging principle is the thing that is not stated. There's no assumption on x and y to be independent or anything like that. I guess if they were independent, you could even simplify things. Okay. So let's apply this averaging principle to our probability here. We'll pick as the event where the variable we want to fix is set 2, all this long string of random bits, and the thing that we keep random is set 1. And so the event is exactly what we had before. The circuit on these previous bits is this predicts correctly the next bit. And if we apply the averaging principle, it means there's a fixed choice, little set 2, so that this inequality from above is is still fulfilled, this one, right? Here it was stated with probability over all of set 1 and set 2. And now I'm using it to get the same inequality, but for a specific choice of set 2. Of course, I have no idea which ones, but they exist. So here we can again, I kept the notation here. F is still computed from this subset as picking certain positions in the capital set. But capital set now is not really as random as before. It's only random on the first n positions, and the rest is this fixed string. Okay. Now we're using, these are still dependent random variables, so it's not clear if we can compute this probability further. But what we know is that our sets I1, I2, and so on come from an L&D design, a combinatorial design. So they have at most d bits in common. In particular, each of these f's up here can only depend on d bits from set 1, because our one of the sets is exactly the first n bits, so all the others can only use d of those. And that means, well, the other n minus d are fixed to whatever is in set 2. And that means all of those, these first, I guess there should be a j less or equal I minus 1. For these first f's, these are all, with a fixed set 2, functions of at most d variables. The rest is hard-coded. And that means whatever this is a Boolean function with d variables. The rest is constant. So you can always write down, say, the conjunctive normal form formula will have essentially this size at most. Maybe can be written much more concisely, but you'll never need more than essentially all the possible, like you do this truth table and read off. Each row gives you the and of all the variables, and then you get an or of all the ones. That's your formula. You can read this off in with a simple algorithm. So in specifically, this means each of these f's can be computed with a small circuit of this size. Now we're almost done. We have all of those circuits. Now this is not a circuit for f, right? Don't get me wrong. This is only a circuit of f evaluated with a lot of the variables fixed to specific values. So that's not a contradiction to f being hard for circuits, not yet. But we can take all of those circuits for the pseudo-random bits that C gets together, all of those written next to each other. In the worst case, that's up to m of those. And we also take our circuit C. So that's a long while ago. Let me go back up here. So that's this assumption. We started with assuming NW is predictable. So there is some circuit C that simulates the prediction of the next random bit. That was the assumption. And the size of that circuit is bounded by m. And well, we're using this part here. If you look at what m is, it's 2 to the d divided by 10, and s as of is at least 2 to the 2d. So there's actually a lot of slack in this inequality here. But that's sufficient for that argument. So we have the m copies at most of this little circuit. And then we have the circuit C from before. That's C. And in total, that's at most S, at least if you make the input size big enough. So you take all of those together. That's one big circuit now. We call it B. And B has the property that it only takes the random variables from set 1 as input. Depends on nothing else. And it computes f of z, the thing on the right, with this probability, the same as before. I'm just inserting what m is. And using how m and s relate, you get this inequality. And now that means we've built a circuit that computes f on, well, random variables, but if you take the average over all possible inputs, you compute it correctly with a good bit more than half of the inputs. And that's exactly what is not possible, because we have this assumption that f has a certain hardness against circuits. So specifically, this was the definition of f, h average of f, in case you remember. So with that, again, we've arrived at a contradiction. A long while ago, we've assumed that the Nisan-Wigderson predictor would be predictable. That brought a contradiction, so that is refuted, which means it is unpredictable, which by Yau's theorem means it produces a pseudo-random output. Oof. So far, this was a sequence of very abstract theorems. So time to make it a bit more concrete. And I've actually not told you the general algorithm. So there's one generic part, and then we'll make it concrete. I'm going to show both already. The generic algorithm, this is just recap. The input, where the setup is, we have some function f, a Boolean function that supposedly has this high circuit complexity. And then from a random seed, we're trying to produce many pseudo-random bits. How are we going to do exactly the construction? Because there's all these parameters we have to pick. In the full general sense, the algorithm is spelled out here. So you pick some n first, and for that you take the largest n that you can pick, so that a certain condition is true. You stay below your input size. And essentially, this comes from the combinatorial design. There we needed L to be bigger than 10n squared divided something, I forget. And that's essentially this inequality. So you pick n as big as you can, but being below this threshold. Then you pick a d so that it matches things. You construct a certain design using the algorithm from back then, which produces 2 to the d over 10 output bits, and then you run the generator on that construction. And by the lemma we've just shown, this is pseudo-random with the specific parameters. Now, if you remember what we actually want to use this for, and the hypothesis about hard functions, we can simplify the construction a whole lot. Yes, the hypothesis back then was there is a function f where the hardness is exponential. And I could have written some constant to the n, but it's more convenient to write it as 2 to the delta n, because everything is happening in the exponent. Then this inequality for L can be simplified, and so effectively you pick n to be like that. If you know your number of seed bits L and you know your delta, then that's a simple function. It's linear in L, so in a way you pick the input size for your hard function is linear in the number of random bits, seed bits that you start with, but it's actually a good bit smaller, right? Delta is probably a constant much smaller than 1, and then you divide it by 100 still. You compute d as well, and this weird expression here simplifies a lot to essentially something linear in n and hence linear in L. Here, this is even more ridiculously small, right? L, the number of seed bits, we should think of them as being logarithmic. Delta is probably a constant less than 1. You square that and you divide by 1,000, so that's going to be tiny. Okay, but asymptotically, it's some growing function. And then we generate from that m bits, which was 2 to the d over 10. So if you put that in, that's the number of pseudo-random bits you generate. And so this is an epsilon that is a constant. It depends on the delta from the hardness, and then divide it by 100 and square the whole thing, so it's going to be tiny. But it's a constant that doesn't depend on L or any other input parameter. All right. And then the guarantee you get, how pseudo-random is it? Pseudo-random against what size of circuit? That you can also express, and you have to check that it's good enough. Which here is a for a pseudo-random generator, we want the guarantee here to be this cube of the output size that was all the way back in the definition. Pseudo-random generator needs to generate some s of n cubed, comma 110 pseudo-random output. And that's where this comes from. So you have to check that your guarantee that you get is bigger than this required guarantee. And that's also working out with these parameters. So very, very long story short, this construction under the assumption that you can have a function f with this exponential average hardness. It gives you a pseudo-random generator with another exponential stretch. And you can even work out what the epsilon is. It's right here. Okay? And that proves this theorem we had a long while back, where essentially this was the claim. All that's left from this unit is a short recap and listing all the facts that we have established, or you will establish in this week's exercise sheet. So the first part here is just some known inclusions among these complexity classes. So they form a nice little sequence. P, the non-deterministic polytime algorithms are contained in those that allow some Las Vegas algorithm randomization, but no incorrect outputs. Then one-sided error Monte Carlo and two-sided error Monte Carlo are even more general. And the unbounded error Monte Carlo was this PP class. But then that class has overdone it. So in a way, it's too powerful. It contains all of NP. So that's going to be the line between potentially practically interesting and certainly practically not interesting. And you'll show a bit more about these one-sided error classes, which we'll discuss in the exercises what the implications there are. The big news is it seems very plausible that P and BPP are actually the same, because you can de-randomize all of BPP. And so any problem, any decision problem for which there is some randomized Monte Carlo algorithm with polynomial time, you can actually find somehow with this non-constructive way a deterministic algorithm. But it's based on this assumption that we have hard functions according to this average circuit hardness. But if that is true, of course, all this hierarchy here collapses and they're all the same, which was one reason why we didn't spend a lot of time on these intermediate classes, because there's good reason to believe, at least from a complexity theory standpoint, they're not so interesting. All right. So what should you take from this, apart from the lovely construction that won some people the Turing Award? You shouldn't try to solve NP-hard problems if all your extra tricks is just randomization. That's very unlikely to work. Or if it works, I mean, come see me and it's probably a breakthrough, but yeah, more likely is there's something not going through. But it still means this doesn't mean that randomness is useless. There's many things you can do with randomized algorithms where we don't know how to do it in deterministic ways with the same kind of qualities and guarantees. So in a way, this this statement is also restricted to what it really says, namely decision problems only, polynomial versus exponential, the big dichotomy. Many things you can still do easier or faster randomized. And also there's some interesting problems at the boundary between complexity classes, where exactly maybe this question is why we can't make progress. And we'll see some examples of that in the next unit. Okay. Any questions about this part? We'll do a little break and maybe just start briefly with some algorithms. Any more votes than the one vote? I'm not sure the sample size is representative of this audience or the general cohort, so it's a bit tricky to get information out of these questions. Nevertheless, it might be useful. Thanks, guys. So we're now completely undecided. It's not really something that fits this module very well, but I might briefly mention what it is, just to so that you at least know what it is and what it isn't. That's quick enough. We spend a lot of time in deep theoretical computer science theory land, which is good fun on my account. But I want to take us back to algorithms at some point. In this next unit, we'll look at some standard tricks or algorithmic design techniques, if you want, that come from randomization and allow you to do things in a certain way better than without randomization. I'll come back to that in a second. I had to pick only some isolated examples. There's many more, and many places have a dedicated lecture just on randomization for a full term. So it'll be a small sample of what you can do with randomness, which kind of fits the topic. But it's not completely random. I gave it some thought. Anyways, so we've seen probably complexity theoretic, not too much to win, but we can still get algorithms that are simpler, even if they don't achieve better performance. Or we could achieve algorithms that improve performance. We've seen very far back the example of median selection, right? So it can be provably more efficient to use randomization, even if it doesn't get you from exponential to polynomial. And it can also improve robustness, which in practical terms is often a very effective way to use randomization. And quicksort with random pivots would be the basic example of that, but there's many more. So here, as I said, just a collection of some examples that illustrate techniques. And specifically, I want to show how fingerprinting and hashing is used, and that's where Bloom filters fit very well. Another thing is, whenever you have a problem where you're trying to show some property and there's an abundance of witnesses, you may be able to just guess a random thing and try to show that it is a witness. Witness in the sense of a certificate for proving some property. Is a bit, yeah, we'll come back to that. And random sampling generally means to pick an object at random. If you have a good chance that that object is what you want, then that's an effective strategy. I guess this will make more sense on the concrete examples. The first thing I want to briefly look at is hashing. I didn't dare to ask who knows hash tables, but this is a very standard undergraduate algorithms topic. So I will only briefly recap some of those bits and rather show a few cases where really the randomized angle comes through and maybe some analyses there. We may just have time for that today. What's the overall setup? In abstract terms, often think of building a dictionary, what you could solve with a binary search tree. You have objects that come from some large universe of possible values, say all strings or something of that sort. A huge possible universe. Here we'll already assume that this is somehow mapped to integers, but it could be a very generous mapping that just translates things into binary strings, and then binary strings can be interpreted as integers. So U is the size of this universe, but we're expecting to only deal with a very small subset of this at any point in time. The actual input size is N, and these, I guess these items come from U. That would have been useful to add. But we think of the number of items that we have to be much smaller than the size of the possible values that we could have. And that's the case where fingerprinting can help in various ways. We'll pick fingerprints from yet another parameter here. So U, the size of the universe, N, much smaller than U, the number of things we actually have. And independent of N, we could pick M for the size of the possible fingerprints that we allow. And then conventionally called a hash function is some mapping from the universe to fingerprints. Now clearly, because we also think of M to be much smaller, H will have collisions. Meaning there are X and Y in the universe so that they have the same hash value. That's inevitable if we reduce the large universe to a much smaller range. And in general, we will have some collisions, yes, but we'll actually have many collisions. The point is that we hope to have few on the actual data items that we deal with. All right. Classic examples of using hash functions for various problems are hash tables and Bloom filters. So a hash table let's maybe draw this briefly. Also do the analysis next time. So for this course, the hash tables I'm thinking of are very simple indirect chaining hash tables. What I mean by that is that the hash table itself is just a collection of buckets. So these are slots that are named by the possible fingerprints up to m-1. The elements from our universe is much bigger universe U, right? They are mapped by H to some of these slots. Here's our X. It's mapped to H of X. And then here we just store a linked list of elements that hashed to this slot and that we store. And maybe then there's a null pointer. That's what I mean by an indirect chaining hash table. I don't care too much how you exactly store this, all the elements that hash to the same bucket. For now, let's suppose it's just a linked list. It's good enough for what we need. So the key property there is that for performance of such a hash table, the key interesting question is how big are the buckets? Or more formally, I think we'll always denote this by capital X for a fingerprint J. It's the number of keys in our. Well, I don't think it's a set; it's a number. So the number of keys with hash value J. In our hash table. So of course, over the entire universe, there's many more, but we care about the elements that we want to store. Okay. Second big application of this fingerprinting is bloom filters. The picture looks almost the same, but it's used for something different, and so also restores things differently. We still have these rows or slots. 0, 1 up to m minus 1. We also have our big universe mapped via h to some slot. But now here, this is a binary vector. We only store zeros and ones. And the way a bloom filter works is it's a fuzzy set, or an approximate membership data structure. You can tell us whether it's potentially true that some element is there. And it's easier to work out if you insert an element x, then if this is our hash table, insert just sets the appropriate position. So you hash x, and it sets that to 1, no matter what it was before. And that's pretty much all it can do. We can then do query, and that just returns the value there. And that's what the basic bloom filter does, which means if I ask a bloom filter, has someone inserted this value x, it might tell me yes, even if actually it never was inserted, just something else that hashed to the same value. So an output 1 can be wrong, can be a false positive. So you might wonder, when would you ever want to use such a thing? But I'll tell you in a second. The nice thing is if it says 0, you're sure this is always correct. Because if nobody hashed to that place, then certainly the thing that you're currently checking also wasn't inserted. Otherwise, it would be a 1. Now you can, there's many ways. So the basic version that I'm explaining here is not working well because it's too probable that something hashes to the same values. It has a high false positive rate. You would want to include several independent hash functions and several bits, and then check all of them. And only if all of the hash tables are 1, you would say this element is present. So you can reduce the false positive rate by using several bloom filters in parallel if you want. You can even use several hash functions, but one big table H. And so you could have collisions between the same values with different values with the same hash value, with the same hash address, or different positions with different hash functions hashing to the same value. You can still deal with that. And there's also ways to somehow make deletions work. In the pure form, you cannot delete something. Once it's been inserted, we cannot remove it again. And the reason is clear. If you wanted to remove something, if you don't know for sure whether it was there before, you don't know whether taking it away, putting it to 0 would delete effectively many other things as well. Right, so bloom filters are like this. They are fuzzy, they can be wrong. In this case, they can only have false positives. So a standard application for this would be some kind of segmented data structure or database where you have your data is too big to be stored in one place, so you split it up in different parts. Now, you could ask the big database, is this element in your portion of the data? And it will tell you, but it's an expensive operation. So instead, you can have a Bloom filter over all the data that's stored and ask the Bloom filter first. And if the Bloom filter says no, then you don't even have to check the database. But if the Bloom filter says 1, you still don't know, you still have to check. But at least then there's a good chance it's a true positive and the effort was worth it. So it's kind of a cheap first check, whether it's promising to look do the expensive true query. That's Bloom filters. So I'm only thinking of a query. I would so you have some database split up according some rule, but you don't know where elements are. Now you're trying to do a lookup, find me the value stored for a key. Then you can ask the Bloom filter of each of the segments, is that key stored in your portion of the data? And if it says no, you don't have to check. If you insert, then you would pick one of the portions and in the Bloom filter of that portion insert. Is that what you meant? There's many more sophisticated versions of this. So in practice, maybe the standard Bloom filters wouldn't be the choice. But that's the prototypical application of hashing there. Okay. Let me just give you a bit of the plan for what we're going to do on hashing, and then we might have to stop. There's essentially 3 ways in which randomization helps hashing. One way is hashing always has a terrible worst case. If you look at either the Bloom filter or the hash tables, if the universe conspires against you, everything will map to the same spot, and you'll get the worst case will always be everything maps to the same bucket. So x1 is n, and all the others are 0, and then the whole thing doesn't work at all. And similarly, in the Bloom filter, you could have everything mapped to the same thing, you don't get any information. But that's astronomically unlikely to happen in most cases. And in particular, if you just test practical data with some halfway reasonable function, even if you're not super clever, it often works out fine. So one way how randomization helps there is to formalize an assumption about the data, and then analyze probabilistically what the guarantees for the data structures are. Now, undergrad, you would do expected values only. We can also do with high probability. In many cases, you get more reliable guarantees there. That's one way. In the analysis, you can use it, and that's uniform hashing is this assumption that all hash sequences that you get are equally likely. And here it's really the hash function for a specific hash function that you pick. You get a collection of elements from the universe, say n of those. And how many are there? If you have m different choices of values and you pick n elements, come on. Hash sequences are equally likely. This is an extremely strong assumption because it doesn't just say something about the input, but it's the combination of hash function and input. Then the other The other two uses are using randomization explicitly to pick a random hash function so that you can expect good performance even if the input is adversarial. And lastly, we'll see some example of probabilistic method turned into an algorithm for perfect hashing. Okay, more on that then next week.